hear you. So just 1 second. I'm so sorry. I forgot to start my video. So just give me quick thing here. So dy over dx equals 2x over y. I cross multiplied and then I integrated, and then we get the left hand side this, the right hand side this, multiply by 2, and this is the answer. We can replace 2c by c1. And when we take square roots, we have to write plus or minus. Okay, got it. Now it's recorded. Sorry, I just, for some reason, I forgot to start the video. Yes. I couldn't understand because I think two of you spoke at the same time, which I'm super happy, but I didn't, do you have something in mind, or you want me to select? Or you want to select from the book?
Can we get one from the book, please?
Yeah. So let me see the page. This is under limits. And this page number. Page number 1 of them, one set is at 126, in which we are not really asked to graph, but we are asked to determine if the function is continuous or not. But yes, 114, same thing. It doesn't matter. We can work on 68 if you'd like, and then we can conclude, which is important, if the function is continuous, differentiable, and find the derivative. If that's okay, we can start with 68. If not, we can look at page 114, where we have all these. Again, here we are asked to find the limit, and the question will ask you to graph the function. So if you'd like to select, go ahead.
Can we start with 73?
Yes, of course. But remember, we had at least 5 or 6 problems similar to this one in the recordings, just in case you need more to look at. Negative x plus 4 for x less than 3, and x minus 3 for x greater than 3. So if you remember, we have to start by identifying the domain. So this changes into negative infinity 3, and this changes into 3 to infinity. So obviously the function is not defined at 3. So when I create the table, I have to have 0 in the table always, and 3, and you will have this, and nothing under 3. Okay? So from negative infinity to 3, we will have to use negative x plus 4. From 3 to infinity, we have to use x minus 3. When I plug in 0, I have 4. When I plug in 3, I get 1. And I write it exactly inside the parenthesis, not under 3, but this time it's to the left a little bit of 3. Then here I have 0. And at 4, I have 1. Since they are linear functions, I don't need more points. This is good enough. So now I can already state many things. Number 1, the function does not have a limit at 3. As x approaches 3 from either side, it does not have a limit. It has a limit from the left, which is 1. It has a limit from the right, which is 0. But from other side, the limit does not exist. So it's not continuous at 3. And it does not have a limit at 3. And it's not even defined at 3. Okay, so now we are ready to graph this function. So 0, 4, 3, 1, and this is the first piece. I normally put the marker down and use a different one, a different color, just to make sure. So this is 3, this is, sorry, it happens at 3, not at 1. Sorry about that. So 0, 4. This is still correct. And now 1, 2, 3, 1. And this is it on the left-hand side. You do not have to use two colors. I'm just making a point. So at 4 is 1. And at 3 is 0. But what you cannot do, you cannot make these overlap. If you write something like this, and I've seen it all the time, this is not a function, is not acceptable. I cannot give credit for this. When the function clearly states this piece exists only between these two, and this piece exists only between these two. Good. So the function does not have a limit at 3. The limit from the left is 1. The limit from the right is 0. And that is its graph. Is it differentiable? Well, I can find its derivative. It's differentiable on the left, which is -1 for x less than 3, and is differentiable on the right, which is 1 for x greater than 3. But it's not differentiable everywhere because it's not continuous everywhere, and because that's it. It's not continuous everywhere, so it's not continuous at 3. So this graph does not have anything to do with calculus. This graph comes from intermediate algebra. The concepts of the limit and derivatives, yes, they do come from this class. Any questions on this problem? Okay, do you think we need anything else? Okay, should we move on to the next topic? Should we look?
We can move on.
Okay. So let's look at some limits. The limits, I'm looking at the page number 124. Good. So let's select anything you'd like to look at as limits. So these are limits from polynomials, limits from rational functions, limits from rational functions, limits from rational functions, again, rational functions and radicals, and then limits from the graph. Any preference, or I will choose?
Can we do 17?
Of course. So let's do 17. In 17 on page 124, we have limit as x approaches 3 from either side of x squared minus 8 divided by x minus 2. So every time we're asked to find a limit, I would say 99% of the time, I have to plug it in from the very beginning. Sometimes in certain situations, I will not be able to plug it in from the beginning. But this is always on our minds. I'm asked to find the limit. I want to know what's going on before I decide the next step. So when I plug in 3, I get 9 minus 8, which is nice. And when I plug in 3, I get 3 minus 2, which is 1, which is nice. I don't have to do anything. There is no need for any strategy here. I don't even have to think. The top approaches 3, the bottom approaches, the top approaches 1, the bottom approaches 1, 1 over 1 is 1. Is this okay?
Yes.
Okay. Very good. Let's continue with another type of problem or another limit. Good. Oops. So the idea is always again, in certain situations, I have to simplify the function a little bit before I plug it in. but 99.99% of the cases, I have to plug it in to see what I'm facing. Okay, do we need other limits to look at? Okay, I will choose 32. In 32, we have limit as x approaches infinity from 7x plus 5 divided by 3x. So there is a whole technique here. Of course, I have to plug it in, and it's infinity over infinity. If you remember, infinity over infinity, 0 over 0, are situations that have hope. There is hope that the limit exists. In the case of 5 divided by 0, there is absolutely no hope. If you remember, we talked about those cases. So the answer in this case is positive or negative infinity or DNE. But infinity of infinity, 0 over 0, these have hope. Because it's the same degree over the same degree, we have a shortcut from a previous class. Or let's say we forget what we studied in the previous class. So then I have to factor out the degree. The degree is 1. They are both linear functions. So when I factor out x, in parentheses I have 7 plus 5 over x. 7 times x is this, so x times this is 5. Of course, I'm going to simplify the problem. This is the problem. This is the problem that creates infinity over infinity. And I know that 5 over huge approaches 0. 5 over huge approaches 0. So then the answer is 7/3, which happens to be the horizontal asymptote of the rational function. Yes, we do know the answer from the very beginning because same degree over same degree when x approaches infinity, it's the leading coefficient over the leading coefficient. We know this from a previous class. In case you forgot, it's okay, but you have to use the technique that we studied in this class, in which we have to factor out the degree, simplify it, because that's the whole idea, and then make sure that we remember when we divide anything tiny by huge, the answer is always 0. I would say approaches 0. Good. Okay, let's see if we need anything else. Anything else we want to look at when it comes to limits? Anything else? Okay, I'd like to look at 22. Any questions so far, please? Stop me if you have questions. Any questions? Okay, well, in 22, we have limit as x approaches -2 from x squared minus 2x minus 8, everything divided by x squared minus 4. There is nothing I have to do right now. I can immediately plug it in. I have to plug it in. So this is 4, and this is 4, and this is 8, -8. 8 plus minus 4, 8 minus 8 is 0. 4 minus 4 is 0. There is hope. Like similarly with the previous case, in which I tried to eliminate the problem, I'm going to try to eliminate the problem here. What does this mean? When I plug in into a polynomial a number and I get 0, it means that the polynomial is factorable, has a factor of x plus 2, x plus 2. So this should look like x plus 2 times something, and this one should also look at x plus 2 times something. How come? Because when I plug in if you remember the remainder and the factor theorem, when I plug in a number in a polynomial, any polynomial, and I get 0, It means that x plus 2, in this case, if it were 2, then it would be x minus 2. So x plus 2, when I move it to the other side, is a factor. So of course here I know the other factor is x minus 2, and here this should be x minus 4. How come? Okay, so let's check. X squared minus 4x plus 2x, 2 times negative 4. And I know that this is factorable. I am able now to eliminate the problem. This is the problem. And now everything is beautiful. Negative 2 minus 4 is negative 6. Negative 2 minus 2 is negative 4. I simplify and I get 3/2. So this is another situation in which I got either infinity over infinity or 0 over 0, and I was able to remove the problem because there is hope. Sometimes I can, sometimes I can't. In which situation I will not be able to. So here's a situation. If I change the problem a little bit, limit as x approaches negative 2 from the same thing at the top. But instead, I'm going to put in the denominator x plus 2 squared. I will not be able to eliminate the problem in this case. I still have 0 over 0. There is still hope, but it's not going to work this time. I will factor the numerator again, exactly what we did before. I will eliminate one of these two, but now the limit is x minus 2 over x plus 2. The top is nice and beautiful, but the denominator is a problem again. And this, however, cannot be eliminated. It's either this, or plus or minus, or this. It happens that it's D and E because we have to study from the left and from the right. From the left will be negative from infinity, from the right will be positive, so the answer will be D and E. So even if initially we jump up and down, there is hope, and here it worked, well, in this case it didn't. So that's why when I say there is hope, I never say it exists. There is hope that it exists. Good. Do we still need to look at limits, or we move on?
We move on.
Okay, perfect. So let's say the next thing I'd like to determine is a tangent, the equation of a tangent. Okay, so here it is, one example, page 144. Okay. Good. So let's choose any example. Let's say here, choose a function, or choose a function from here, it doesn't matter. And let's determine the equation of the tangent line to the graph at such and such, given the point. So we pick a function, and it gives us the point where to find the equation of the tangent line.
Can we do 18?
Yes, of course. So let's look at 18. Find the equation of the line to the graph of f of x, very simple. F of x equals x squared, and this is page 144. And choose any point, or we can make one up, any point. We don't need to do all three. Just choose one point or just make one up.
We just do 3, 9.
Very good. Okay. So remember, the equation of a line is y minus y1 equals the slope times x minus x1, where I have 3 and 9. What I don't have is the slope of the tangent line. But that's very easy because I need to find f prime of x, which is 2x, and I need to plug in 3 in it. And that will be the slope that I need. So f prime of 3 is 6. So the slope is 6. And I have to solve for y. So y minus 9 equals 6x minus 3, 6x minus 18, and plus 9. So then y equals 6x minus 9. What is this again? It's the equation of the tangent line to the graph of x squared exactly at this point. So if the graph looks like this of x squared, and let's say this is the point 3, 9, this is the equation of the tangent line to the graph of f of x equals x squared. Notice that intentionally I did not put a coordinate system, so I don't have to write the graph anything exact, just to explain. So this is y equals 6x minus 9. So this is very important. Why is it important? As you noticed in this class, we were interested in the equation of the tangent, or mainly the slope of the tangent, because that's how fast this function is growing or decreasing, if it's on this side, growing at this point when x is 3. Good. Of course, we have these types of problems in chapter 2, in chapter 3, with exponentials, with logs, but the idea is exactly the same. You're given a function, you find the derivative, you plug in x, and that's your slope. Good. Do you think we should look at another example? Maybe with another function, or we move on to another topic. Please